Hello everyone, I Dr.B.D.Karande, Head Department of Mathematics, Maharashtra Udayagiri Mahavidyalaya Udayagir. Today's discuss on the unit number 2, open sets, closed sets and countable sets. In this lecture, we will learn to some points. That is, the first point is the neighborhood of a point, deleted neighborhoods, interior point of a set, open set, some examples. First, what is the neighborhood of a point? Suppose that a set n is the subset or equal to R. R is the real number set, is called, this subset n is called the neighborhood of a point A if there exists an open interval I. There exists an open interval I containing A and contained in n, that is the A belongs to I is the subset or equal to n. Then this n is called the neighborhood of a point A. It follows from these definitions that an open interval is the neighborhood of each of points. By these definitions, we says that any open interval is the neighborhood of a point, each of its points. We take the open interval, that is the open interval A minus delta, A plus delta, where delta greater than 0 as the neighborhood of a point A. Next, what is by the deleted neighborhoods? The set is the set of x such that 0 less than x minus a less than delta. This is the open intervals. Okay, but that is an open intervals a minus delta, a plus delta, from which the number a itself has been excluded or deleted, is called the deleted neighborhood of a point A. Note, for the sake of brevity, we shall write the neighborhood as a short form. This is the neighborhood in the short form, it is the NBD. Okay. For examples, the set R of the real number is the neighborhood of each of its points. By the definition, for every point of the real number set, there exists an open interval which contains this point and contained in R. Therefore, this set R is the neighborhood of each of its points. Second, the set Q of the rational is not the neighborhood of any of its points. By the definitions, suppose that the x is an arbitrary point of the rational number set Q, but there is no exist the interval, open interval which contained in Q, because the every open intervals contains the rational as well as irrational numbers. Therefore, this Q set is not the neighborhood of the each numbers of this set. That is, the Q is not the rational numbers. Means that is, the Q is not the neighborhood of the each of its point. Okay. Next, the open interval AB is the neighborhood of each points, because this open interval is also the neighborhood of each of its points. Another one examples, the closed interval AB is the neighborhood of each of point, this open interval. Okay, this closed intervals is the neighborhood of each of its only point, this open intervals, but it is not the neighborhood of the end point A and B. By the definition, there is no exist the open intervals which contains these end points contained in this closed interval. Therefore, this closed interval is the neighborhood of the only these points of the open interval, but it is not the neighborhood of the end points A and B. Another one example, the null set phi is the neighborhood of each of its points, in the sense that there is no point in phi of which is not the neighborhood. First examples, a non-empty finite set is not the neighborhood of any points. Solution of these examples. A set can be a neighbor of a point if it contains an open interval containing the point. Since an interval necessarily contains an infinite number of points, there is the rational as well as irrational numbers. And therefore, in order that a set be a neighbor of a point, it must necessarily contains an infinite of points. Thus, a finite set cannot be a neighbor of any points. Another one example, superset of a neighbor of a point x is also a neighbor of x. That is, if n is the neighbor of a point x and m contains n, m is the superset of this n, then m is also the neighbor of x, because every point of this n set there exists an intervals which contains each point, and this contained in this n, but n is the subset of or equal to n, means that is the each point of n there exists an intervals such that x belongs to, suppose x is an arbitrary, x belongs to intervals ix is the subset of or equal to n, but n is the subset or equal to m, means x belongs to ix is a subset or equal to capital M, means the capital M is the neighbor of the x. But x is an arbitrary point of the set n, means the m is the neighbor of each of its point, means there is a superset of the neighbor of a point x is also a neighbors. Another one examples, the union finite or arbitrary of the neighbor of a point x is again a neighbor of x. Next example number 4. If m and n are neighbor of a point x, then show that the intersection of these two sets is also a neighbor of x. Since m and n are the neighbor of x, the m and n are the neighbor of x, by the definition there exists an open intervals including the point x such that, means the first m is the neighbor of x point, means x belongs to this open intervals subset or equal to m. n is the neighbor of x, means that is there exists an open interval such that x belongs to this open interval subset or equal to n. This is the in the diagram form on the real lines, and this real lines is connoted in the diagram forms. This is the m set, this is the m set, and this is the n set, and these two set is connoted in the diagram forms. So that is the m, and suppose this is the n set. Okay, and this x point, this is the x point. There exists an open interval. This is the open intervals contained in m set. Okay, another x belongs to this second open intervals contained in the set n. Okay, let delta is equal to minimum of delta 1 and delta 2. Find the delta is equal to minimum of delta 1 and delta 2. Suppose that delta 1 is less than delta 2, and the minimum of this, that is the delta 1. Suppose that delta 2 is less than delta 1, then the minimum of these two, delta 1 and delta, that is delta 2. Okay, take any delta is equal to minimum of delta 1 comma delta 2. Then again this number, this point x belongs to this open interval, but this open interval is the subset or equal to this open intervals, and this open intervals, that is the subset or equal to m, and similar, that is the this open interval delta is the minimum of delta 1 and that is the subset or equal to this open interval, but this open interval is the subset or equal to m. This implies from these two relations, that is this open interval, means x belongs to this open interval x minus delta x plus delta is the subset or equal to intersection of these two sets. This is the intersection of these two sets. X belongs to this open interval is the subset or equal to the intersection of these two sets. This is the part of these intersections in this figure, and hence the proof. Next point, the interior point of a set. What is by interior point? A point x is an interior point of the set S. If S is the neighbor of x, means S is the neighbor of x, then x is called the interior point of the set S. In this figure, point x, okay, x is the means S is the neighborhood of X point because there exists an open intervals. They are contained in S. Therefore, by the definition, S is the neighborhood of X. Again, by this definition, X is called the interior point of the set S if S is the neighborhood of X. This S is the set is the subset of the real number set. Okay. In other words, X is the interior point of S. If there exists an open interval, another word, X is called the interior point of the set S. If there exists an open interval, this is the open interval containing X and contained in S. That is the X belongs to this open interval, belongs to, that is the subset, so not belongs to, that is subset or belongs to, subset or equal to S. Thus a set is the neighborhood of each of its points because X is an arbitrary point. This set S is the neighborhood of each of its points. Okay. Next, what is by the interior of a set? The set of all interior points of a set is called the interior of the set, and the interior of the set is generally denoted by this S dash. Another, that is the INT, interior, short form, that is the INTS. For examples, the interior of the set N, natural number set. Natural number set is the neighborhood of each of points? No. Okay. There is no interior point to the natural number set because N is not the neighborhood of each of its point. Integer set is also not the neighborhood of each of its point. Also, rational number set is also not the neighborhood of each of points. Means the interior set of the natural number set, integer set or rational number set is the null set by the definition. But the set R is the real number set, is the neighborhood of each of its points. Means that is the every point of the real number set is the interior point, are the interior points. Therefore, interior of R is the itself R. Second example, the interior of the set S is the subset of S. Is that correct? Because the some sets, all points is an interior point, but some set, not all points is an interior, some points, okay, only the interior point. Means that is the interior set is the subset or equal to S. That is the next heading by the open set. It is an important concept in this unit. First define the open set. A set S is a set to be open if it is the neighborhood of each of points. Okay, means the every point of this set S is an interior point. Or in other words, if the set S is the neighborhood of each of its points, then this set is called the open set. From this figure, suppose this is the set S and X is an arbitrary point. That is, for X belongs to S, there exists an open interval Ix such that X belongs to Ix is the subset or equal to S. Means the S is the neighborhood of X, but X is an arbitrary point. Means the S is the neighborhood of each of its points. Okay. And therefore, this set S is the open set. Thus, every point of the open set is an interior point, so that the open set S means that the interior set is equal to S. Okay, this is the second condition of the open set. That is the S dash is equal to S. Means the set of interior points is equal to S. Then this set S is said to be open set also. That is the S is the open implies that is the S is equal to S dash. Of course, the set is not open if it is not the neighborhood of at least one of its point. At least 1, 2, 3 or many. But at least one of the points is not interior point, then this set is not the open set. Or that there is at least one point of the set which is not an interior point. For examples, the set R of the real number is an open set because R is the neighborhood of each of its points, or every point of the set R is an interior point. Therefore, by the definition of the open set, the real number set is an open set. Second, the Q, rational number set is not open set because every point of the rational number set is not an interior point. Q is not the neighborhood of each of its points. Therefore, by this definition says that Q is not the open set. Similarly, the closed interval is not open because there are 2 points. The end points A and B are not the interior point to this closed interval. Therefore, by the definition says that this closed interval is also not an open set. The null set phi is the open, or there is no point in phi which it is not the neighborhood of this any point. A non-empty finite set is also not open set because every non-empty finite set is not the neighborhood of each of its points. Every points of the non-empty finite set is not an interior point. Therefore, this non-finite set is not an open set. This set is also not open set. Okay. Next, the example number 5 says that show that the every open interval is an open set. Every open interval is an open set. Find the solution of, or the another statement, every open interval is the neighborhood of each of its points. These two are the meaning same. And the solution of these examples, let x be any point of the given open interval AB. Okay. So that we have A less than x less than B. This is the interior. X is the point of the open interval. This is the arbitrary point. On these real lines, this is the open interval AB. A and B are the end point of this open interval, and x is the point of this open interval AB. Let C and D be the two numbers such that the A less than C less than x and x less than D less than B. So that we have A less than C less than x, also x less than D less than B. Okay. Thus, the given interval, open interval AB, contains an open interval containing x. Means this open intervals contains the open interval CD containing the point x. Okay. And therefore is the neighborhood of x. Therefore, this open interval AB is the neighborhood of x, but x is an arbitrary point. Means the open interval is the neighborhood of each of its points, and therefore this is the open set. Okay. One examples. Every point of an open interval is its interior points. Open interval is the open set, means that is the every point of this open interval is also an interior points. Another example, show that the every open set is the union of the open intervals. So that every open set is the union of the open intervals. Let S be the open set and x lambda a point of S. Okay, S is the open set and x lambda is a point of S. Since S is the open, by the definition S is the open, means therefore there exists an open interval I x lambda for each of its point x lambda, such that x lambda belongs to I x lambda is the subset or equal to S for all x lambda belongs to S. By the definition, this is the diagram of this. This set S is the set of the real number, subset of the real number set, and all these are the open intervals for each points. Okay, that is the, suppose this is the x1 point, its open interval is x2 point is the x3 so on, this is the x lambda and x lambda. Suppose this is the x lambda and the x lambda belongs to these open intervals, and this open interval contains the whole set. Okay. Again, the set S can be thought of as the union of the single sets, that is the for each single element set x1, x2, x3, so x4, so on x lambda. S can be thought of as the union of the single sets like that is the S is equal to union of the single element set x lambda, where the capital lambda is the index set. Okay. Therefore, S is equal to union of this single element set x lambda, but each single element is contained in the each open intervals, that is the Ix lambda. That is the Ix1 which contains in the Ix1, x2 which contains in the Ix2. See, so in general, that is this is the subset or equal to union of Ix lambda. But the union of all these intervals, that is the subset of or equal to S. Okay, and this implies S is equal to the union of Ix lambda. Means the every open interval, open set is the union of the open intervals. In this lecture, we learn to the first point, what is by neighborhood of a point. Second, what is by related neighborhoods. Third is the interior point of a set. Fourth is the open set. Some examples on the open set and interior point of a set.